In the last few lectures, we had examined the stress tensor and the rate of deformation or the velocity gradient tensor in a Cartesian coordinate system. So, let me briefly summarize that before I go on to the constitutive relation. Okay. So, first is the stress. Okay. Second order tensor has two directions associated with it. Has two directions associated with it, and Ex. Okay, the first set of unit vectors on the left and the first index is the direction of the force. Stress is a force per unit area. So, the direction of the force is given by the first index in the first set of unit vectors on the left. So, if I have some surface here, and that surface is perpendicular to a unit normal n, okay, and you have some force acting at that surface F. The first index refers to the direction of the force per unit area at that surface. In the limit, as the surface area goes to 0, the force decreases proportional to the surface area, and the stress is a constant. The ratio of the force and the surface area is a constant. First index refers to the force, second index refers to the direction of the perpendicular to the surface. Okay. So, the force per unit area at a surface will be written as at a surface is equal to this stress dotted with the perpendicular to the surface. Okay. So, the force depends upon the orientation of the surface. Okay. That is obvious. If the surface is perpendicular to the flow, you will have a larger force. If the surface is parallel to the flow, the force will be less perpendicular to the surface, and so on. However, the stress, the components of the stress are uniquely specified at each location. So, the stress is a field variable, a second order tensor field variable, which comprises of 9 scalar components. Okay, for 3 values of x, y, z for the force direction, and 3 values of x, y, z for the direction of the perpendicular to the surface. So, that is the first component, that is the stress. We had seen that the stress has to be symmetric. Okay. Is symmetric. For angular momentum. Balance. Okay. Angular momentum is satisfied for a differential volume only if the stress tensor is symmetric. Okay. And in the absence of flow, we had seen that the stress tensor can be written as sigma is equal to minus p times the identity tensor. Okay. So, in the absence of flow, there is only fluid pressure. Pressure is a compressive force. It acts perpendicular to the surface. Okay. So, it is always oriented perpendicular to the surface along the inward unit normal, whereas the stress here has been defined relative to the outward unit normal. That is why there is a sign minus p here and times the identity tensor. So, for any surface, okay, in the absence of flow, the force is always acting in the direction perpendicular to the surface, and the magnitude of the force is the pressure along the direction perpendicular to the surface. pressure is a scalar uniquely defined at each position. The force on the surface is equal to minus the pressure, and it acts along the perpendicular to the surface, and therefore, the force depends upon the orientation of the surface. The pressure is independent of the orientation of the surface. Okay. In the presence of flow, there is going to be one additional term here. Okay. I will call that as the shear stress, the pressure plus the shear stress, and this second component has to be necessarily symmetric because of our requirement that the stress tensor is symmetric. Okay. So, there can be no antisymmetric part of the stress tensor. An antisymmetric part would not satisfy balance of angular momentum. Okay. So, that is the first part. Okay. The stress consists of an isotropic and a symmetric part. Okay. What about the second part, the strain rate, rate of deformation, okay, velocity gradient or the rate of deformation. Okay. This is also a second order tensor, the gradient of the velocity, okay, which can be written in long form as E x, E y, E z. There is the velocity gradient of the rate of deformation tensor, and I had physically explained this to you, okay, x, y and z in 3-dimensional space. If I have 2 points separated by a distance delta x at the location x and x plus delta x, okay, separated by displacement delta x, the difference in velocity, okay, v at x, v at x plus delta x, okay. The difference in the velocity v at x plus delta x minus v at x, okay, is going to be equal to delta x dotted with grad v. Okay. This is exactly analogous to, for example, the change in concentration. If you go to a small distance delta x, the change in concentration is delta x dotted with grad c. In this case, the first unit vector corresponds to the direction of variation or the direction of the derivative. Okay. The first unit vector corresponds to the direction of variation or the direction of the derivative. The second one is the direction of velocity itself. Okay. So, this is the rate of deformation tensor, and we had separated this out into 3 parts. Okay. Is equal to 1 by 3 the divergence of velocity times an isotropic tensor. Divergence of velocity is a scalar plus this second part, okay, the second part which is extensional strain, okay, this is isotropic. This is symmetric traceless. Okay. Plus a third part which is antisymmetric. Okay. Okay. And each of these 3 represents specific forms of deformation. Okay. So, the first part actually represents radial expansion or compression from this location. Okay. So, let me write this as delta x and delta y. Okay. This first part represents radial expansion or compression. Okay. Radial expansion if the divergence of velocity is positive, and compression if the divergence of velocity is negative. Okay. The second part represents extensional strain. Okay. In which you have extension along one axis and compression along the orthogonal axis, okay, in such a way that the axes do not rotate. Okay. The axes do not rotate, and there is no change in volume either. Okay. There is no change in volume, and there is no change in the axis of rotation, and the deformation is extensional along one coordinate and compressional along the orthogonal coordinate. And we had seen that this third part represents solid body rotation. The third part represents solid body rotation. In 3 dimensions, the first part is isotropic. It is radially outward or inward in 3 dimensions. The second part is symmetric traceless. It has 2 directions. It has 3 orthogonal directions in space, which are the principal coordinates along which there is extension or compression. Okay. These principal coordinates, the eigenvectors of this symmetric traceless matrix, are perpendicular to each other, and the rate of expansion or compression is given by the eigenvalues of that symmetric traceless matrix. The sum of the eigenvalues is 0. So, you could have either expansion along 2 directions and compression along the third biaxial extension, expansion along one and compression along the other 2, uniaxial extension or planar extension, which is there is no deformation along one of the axes, and expansion and compression along the other 2. Okay. And the third part is the antisymmetric part, and this represents solid body rotation, where the velocity, the relative velocity between nearby locations delta v can be written as half of omega cross delta x, where omega is the vorticity. Okay. Omega is equal to the curl of the velocity. Okay. The curl of the velocity, or the cross product of the gradient and the velocity. Okay. And so, this represents solid body rotation with angular velocity equal to half the vorticity. So, this has 3 parts, okay, the isotropic, symmetric, traceless and antisymmetric. Okay. Now, when we write a constitutive relation for the viscosity, that is Newton's law for viscosity, this has to be a relation which is independent of the underlying coordinate system, because it is a relation between 2 physical objects, the stress and the rate of deformation. In Newton's law, the fundamental assumption is that the stress tensor is related to the gradients of the velocity. It is a linear relationship in the gradient of the velocity. Just as the flux is proportional to gradient of concentration and the heat flux is proportional to gradient of temperature, the assumption here is that the flux is proportional to the gradient of the velocity, the stress. However, this is a tensor relationship. Okay. So, the stress, you cannot just write it as tau x z is equal to mu times partial V x by partial z, okay, because if I rotate coordinates, then the components will all change. Okay. The left and right sides here will change if you rotate the coordinates. Okay. Therefore, this kind of an expression does not satisfy tensor symmetries. What you have to write is a relationship between the stress and the components, the isotropic, symmetric, traceless and antisymmetric parts of the rate of deformation tensor. Okay. The stress I told you was symmetric. Okay. Therefore, it cannot be proportional to the antisymmetric part of the rate of deformation tensor, because you cannot have a symmetric tensor equal to an antisymmetric tensor, okay, unless they are both zeros. Okay. You cannot have a symmetric and antisymmetric tensors equal. Okay. So, therefore, the stress cannot depend upon the antisymmetric part of the rate of deformation tensor, and that is understandable from physical considerations as well. Okay. If for example, I have solid body rotation about a location, okay, if I have solid body rotation about a location, okay, the material does rotate of course, but the material elements in the solid body rotation do not deform. As the material rotates, the distance between nearby locations within the material remains unchanged. Okay. So, there is no deformation within the material, and therefore, there cannot be a stress generated, because a stress will be generated only if there is deformation. If there is no deformation, then there can be no stress generated. Okay. So, therefore, the stress cannot depend upon the antisymmetric part of the rate of deformation tensor, which means that the constitutive relation for the stress, this is the shear stress, recall, the total stress contains the pressure plus the shear stress. So, this can have only two components. Okay. It has to be something times the symmetric traceless part plus some other thing times the isotropic part. Okay. Those are the only two possibilities for a relation between the stress tensor and the rate of deformation tensor, okay. Not the components, but rather between the tensors themselves, because as I said, the constitutive relation is a relation between two tensors. Okay. So, this is the only possibility of a relationship between two tensors. Okay. And the coefficients in these are related to the coefficients of what is called the shear viscosity, okay. This is the shear viscosity, and the second coefficient is the bulk viscosity, what is called the bulk viscosity, okay, which is related to the isotropic part, the radial compression or expansion. For an incompressible flow, this isotropic part is equal to 0. Okay. For an incompressible flow, this isotropic part is equal to 0. Okay. For an incompressible flow, okay, the symmetric traceless part, okay, is, recall, half of gradient of the velocity plus its transpose. Okay. Minus 1/3, okay, times the isotropic tensor times the divergence of the velocity. Okay. This is a symmetric traceless part, okay, and the divergence of the velocity has to be 0 for an incompressible flow. Okay. So, therefore, this is just equal to half of divergence of velocity plus okay, for an incompressible flow, okay, which means that the stress tensor is going to be equal to mu into the gradient of the velocity plus the gradient of the velocity transpose for an incompressible. Okay, this is the expression for the stress tensor for an incompressible fluid. Okay. This is Newton's law written in tensor form. Okay. This is basically Newton's law of viscosity. Okay. Note that this is different, okay, from what we usually write over here. Okay. This is different from what is usually written over here. Okay. Here we are writing between the tensor components. Okay. So, therefore, this the term on the right, okay, is going to be equal to, okay, tau, okay, the tensor is equal to mu into 2 partial Vx by partial x, okay, the gradient plus its transpose. Okay. So, this is the actual expression for the stress tensor in 3 dimensions. Okay. For unidirectional flows where Vx is only a function of y, okay, or rather the unidirectional flows that we have been considering, for unidirectional flows, okay, okay, this tensor, okay, you can simplify the expression that we have here is equal to mu into this 0 okay, Vy and Vz are 0 and Vx is only a function of z for a unidirectional flow. Okay, so, let me draw the configuration for you. This is x, this is z, and you have some velocity profile for a unidirectional transport, okay, where Vx is only a function of z. This is the stress tensor. Okay. So far, we have been taking into account only this part of the stress tensor. Okay. But as I said, the stress tensor has to be symmetric. Therefore, tau xz is non-zero and tau zx is also non-zero. Okay. So, that has also got to be included in the momentum balance, okay, when we write down momentum balances. So, this is the extension of the rate of deformation tensor and the stress tensor to a Newtonian fluid which is incompressible. If it is compressible, then you have to include this additional part which is related to the divergence of the velocity. Okay. So, this is the constitutive relation. Okay. So, okay. So, let me write the constitutive relation for the total stress tensor sigma is equal to minus p I plus mu into gradient of the velocity plus its transpose. Okay, that is the expression for the stress tensor. Now, this has to be substituted into the momentum balance equation in order to get the Navier-Stokes equations. Okay, so, the mass conservation equation for an incompressible fluid, okay, I should note that this is incompressible. The mass conservation equation for an incompressible flow is the divergence of the velocity equals 0. Okay. So, that is the mass conservation equation for an incompressible flow. Okay. What is the momentum conservation equation? I will not go into the derivation, I will just motivate the form of the momentum conservation equation for you. Okay. Note that the mass conservation equation, the concentration field plus del dot C V is equal to minus the divergence of J, where J was the flux, okay. J was the flux, C was the concentration and V was the velocity. If I write the momentum conservation equation in a similar manner, okay, I will get partial of rho V, momentum density by partial T plus the divergence of the momentum density times the velocity. Okay. Divergence of CV instead of C concentration, instead of mass density, I am substituting momentum density. Okay. Minus the divergence of J, instead of J I will have sigma, okay, plus the body force per unit mass, which is the analog of the rate of production of mass per unit volume per unit time. The equivalent of that is the body force per unit volume per unit time. For example, for gravitational forces, F will be equal to rho times the gravitational acceleration. Okay, F is the body force density, force per unit volume, which is the mass per unit volume times the gravitational acceleration. Okay. Note that the dot product here, so let me write it a little bit more clearly. I will write this as V times C. In this case, C is a scalar, so it makes no difference, okay, because C is a scalar, it makes no difference. Similarly, I can write this as V times rho V. Okay, now, rho V is a vector. Okay. The dot product is with the first V in front. Okay, the dot product is with the first V in front. Okay. On the left hand side, I can differentiate using product rule. Okay. I can differentiate using product rule. Okay. So, what I will get is V partial rho by partial t plus rho partial V by partial t plus V dot grad of rho V plus sorry okay. My apologies here. Let me expand this out once again. Okay. So, I can take this blue term out first. Okay. If I take the blue term out first, I will get rho V dot V dot grad of rho V, okay, plus rho V dot grad V. Okay. Note that in this term, the dot product is between the divergence and the velocity here. Okay. So, in the first term, I have taken the velocity out while using product rule for differentiation, and I get V dot grad of rho V. And the second term, I have taken rho V times out, and I get rho V dot grad V. Okay. So, yeah, that's better. Yeah. Okay. Yeah. So, this is the expansion using product rule. Okay. And I can combine these two terms. Okay. These two terms. Okay. Recall that my mass conservation equation, I had written it for a constant density system as this one, okay, but actually the initial mass conservation equation that I had was partial rho by partial t plus divergence of rho v is equal to 0. Okay. That was for a compressible flow, and then I had simplified this for an incompressible flow. Okay. You can see that the sum of these two terms is just equal to the velocity vector times this mass conservation equation, which has to be 0 due to incompressibility. Okay. Therefore, if I substitute that, I get rho into partial v by partial t plus v dot grad v plus f is a vector. Okay. Note that I am using 2 underbars for a second order tensor and 1 underbar for a vector. Okay. And now we have to simplify this divergence of the stress. Okay. We have to simplify the divergence of the stress. So, I will continue with this calculation in the next lecture and finally derive the Navier-Stokes momentum conservation equation in vector form. I will continue this in the next lecture. I will see you then.